Okay, good morning, everyone. So I'm going to give you this lecture about geodetic VLBI. So first of all, I'd like to introduce me. So I am Patrick Charlot, and I work at the University of Bordeaux in the southwest of France. And this is on the right. This is the building where I actually work, and where I am currently, actually. And so I've been doing VLBI for a number of years, both on the astronomy sides, but mostly on the geodetic and astrometric VLBI. So this is what I'm going to talk about today. So this will be this is the outline of my talk. So in the introduction, I will just explain what is geodesy and give some information about how the observing scheme and analysis scheme. This will be in general ways. Then I will talk in more details about the modeling. You have to model the quantities that you get from the observations, including some astronomical and geophysical parts. You have to apply some instrumental correction and atmospheric propagation. So I will give you an overview of all the components that you have to model to achieve the analysis. And then I will present what you get actually from these observations. It's a geodetic product. So they consist mainly of three things. The reference frames, I mean terrestrial and celestial frames, and the Earth orientation, the parameters of the Earth orientation. And then I will finish the lecture by talking about the future, and especially talking about the new system that is being implemented. And I mean VGOS, which means VLBI, Global Observing System. So just to start, so what is geodesy? So if I were to summarize, give a definition of geodesy in one sentence, I would say that the goal of geodesy is to measure the shape of the Earth, its gravity, and its orientation in space. So this gives you a full geometry about the Earth and its potential. So how do you do this in practice? And you have a number of techniques that you can use for geodesy, geodetic space techniques. So of course there is VLBI, but there are also satellite techniques, GNSS, which means Global Navigation Satellite System, like GPS. And you also have SLR, satellite laser ranging, where you fire a laser from a station on the Earth to a satellite, and then the signal is reflected and comes back to the Earth, and you can measure the time that it takes, and then infer the geometry of the system. LLR is lunar laser ranging. This is the same thing except that you do this on the moon using the reflectors that were put there by the Apollo mission some 50 years ago. And DORIS is a positioning system from the French Space Agency, which work in similar as to GPS, but well, not like that, but also positioning systems. So as I said, with these techniques, you can monitor the Earth orientation, establish the terrestrial frame, and establish the celestial reference frame. These are the three main products. And I would like to emphasize that VLBI is unique for determining some parameters among all these. UT1 minus UTC, which basically is the length of day. the satellite techniques cannot do this on the long term and with a precision that is similar to VLBI. So VLBI is really unique to monitor the rotation of the Earth. Precession and nutation, this is the motion of the axis of rotation of the Earth with respect to space, so with respect to the quasars that we observe with VLBI. And the celestial reference frame gives you the position of these quasars in the sky. And this is also unique with VLBI. You need radio telescopes to do that. You can't do that with satellite techniques, of course. Just as a small note, there are now, so these are the main techniques to measure the Earth's rotation, the Earth's orientation. But there are some new things that are coming online, like superconducting gravimeters, that are becoming competitive to measuring the nutation. So this is more or less the same thing, except in graphical form. You have can you see the mouse on the screen, or?
Yeah.
Yes, okay. So this shows the terrestrial frame. So basically, it is a set of position of radio telescopes on Earth, position and velocities of your observing sites, and you have time series of these positions, which gives you the velocity of the sites. As I said, you have the Earth's rotation. Then, well, you have the celestial frame, which consists of several thousands, the position of several thousands of distant extragalactic sources, and I mean quasar positions. And in between the two, you have the Earth, the parameters of the Earth orientation parameters, as we say, and they connect the terrestrial frame, which is attached to the Earth, and the celestial frame, which represents directions in the sky. And as I said, you have to monitor the rotation of the Earth, but also the motion of its axis with respect to space, and also with respect to the Earth's crust. And as I said, VLBI is the only geodetic space technique that can measure all this at once. So it's a complete determination of the system. So what are the VLBI quantities, the VLBI observables that you used? Actually, there are two types of observable, those that you use for astronomy and those that you use for geodesy. So just about astronomy, what you use is what we call the complex visibility, which is made of two quantities, the amplitude and the phase. And using these quantities, you can, well, this comes from the interferometer. So this is the interferometric amplitude and then interferometric phase. And using these quantities, you can reconstruct image of the sources with a very high resolution because you have intercontinental baselines. But I will not go in details about this. And for geodesy, you have two quantities that are inferred from the other ones, from the phase actually. So the group delay, which is the derivative or partial derivative of the phase with respect to frequency. And this is what you can see on the right, the plots that you see on the right. You have the frequency here and the phase here. So you measure the phase at a number of discrete frequencies, and then you fit a straight line to these phases measured between, here it's between 8.2 to 8.6 gigahertz, and then you fit a straight lines, and then you get this quantity, which we also call the bandwidth synthesis delay. And you have another quantities, which is the derivative of the phase with respect to time, and we call this the delay rate. And so this is the rate of change of the delay over time. So it gives you the variations of the delay over time. So these are the two quantities that we use in geodesy, but the most important one is this one. and the other one is inferred from that one. So just to give you some feeling about how you run a session, what happens during a session. So typical geodetic session. So you observe at two frequencies, what we call S band, which is 2 gigahertz, and X band, which is 8 gigahertz. And we do this because these are simultaneous observations. And we do this in order to eliminate the effect of the ionosphere, because the ionosphere perturbs the measurements, and we can just, using a linear combination of the quantities at the two bands, we can eliminate the ionospheric effects, and I will say more about that in the modeling part. The sessions usually, well, not usually, a session lasts for 24 hours. So you start, and the reason for this is that you can eliminate, by doing this, some daily effect, some effect that have a 24-hour modulation. So you can eliminate this if you do a 24 hours. It doesn't. Okay. Okay. You usually use, well, 8-10 radio telescopes, or even more. You can go up to 15 or even more, and which you want to spread over different continents, so that you get really intercontinental baselines and high resolution, and then high precision in the data that you measure. You usually observe between 50 and 100 extragalactic sources in various parts of the skies. You need to look at as many areas in the skies as you can, and this is needed in order to estimate the tropospheric parameters over the stations, because your measurement is also affected by the atmosphere, and you need to cover the sky above each station. Again, I will say more later. And so you have these 50 to 100 extract sources, which you will observe several times during your 24 hours. And each observation usually lasts of the order of one to a few minutes. And this is how you do this. So you go on one source, you stay 1 or 2 or 3 minutes, and then you move to another source, and so on for all the direction of your experiment. Network. So I mentioned that you have intercontinental baseline. So this is the current distribution of the current network. So by network, I mean radio telescopes that you use to do this. And most of these radio telescopes are run as part of the sessions that are run by the IVS, the International VLBI Service for Geodesy and Astrometry. So this service its role is to monitor the Earth's rotation, and to establish the celestial and terrestrial frame. So this is why you have regular experiment, especially for the Earth's rotation. You have several experiments per week, so that you can track the Earth's orientation, because it's at some level it is not predicted. So that's why you need to monitor it. And you also the VLBA, the Very Long Baseline Array, which is a network consisting of 10 stations spread over US, including from Puerto Rico to Hawaii. And this network also cooperate with IVS and join for some sessions. So you have some common session with IVS on the VLBA. So what is the analysis principle? So I explain how a session is done, how things are done in practice at the analysis level. So as I said, you observe 50 to 100 sources, and then so your session, since you have 10 stations and many pointings, so usually you get between a few hundreds to several thousands of VLBI measurements, VLBI delays. Of course, this depends on the network size. If you have more stations, of course, you have more stations, you have more observations, of course. So for each quantity that you measure and the observed delay, which I call two ops here, you will calculate an equivalent theoretical quantity, which I call tau m, and so using basically theoretical modeling, and you reproduce the equivalent of the observed quantity. So you calculate this, and then you do the difference between the two quantities. So you have one observed quantity and one calculated quantity. And then you apply the usual least squares method to minimize the differences, to minimize the sum of the square residuals of these two quantities. And this is the principle of the least squares method. And you vary some parameters and you try to adjust them so that you can get the smallest value for this sum of the square residuals. And then you can, well, I said you estimate some parameters, but you can have, there are different types of parameters depending of your interest. But you need at least to estimate the clocks, linear or quadratic clocks. What I mean is that at each station you have a clock that gives you the precise time, but these clocks are not perfectly synchronized on different parts at different stations, and at the level of the accuracy that you work. This is not enough. So that's why you estimate the difference or the parameters of these clocks. So, and in the same way, you also estimate the tropospheric parameters. So the troposphere is the layer, the atmospheric layer that is start from altitude 0 to maybe to 10 kilometers or so. And so this is the closest layer, atmosphere layer to the ground. So you must estimate these clocks and tropospheric parameters because you cannot model them very well. And then depending on your objective of your experiment, you can estimate the Earth orientation parameters or the station coordinates, the radio telescope's coordinate, or the source coordinates, the quasar's coordinate. So this gives you an overall view of the geodetic analysis with VLBI. Okay, so now I'm going to go with explain in details the modeling, how you model these tau quantities, this delay, these group delays. But first, maybe we can stop for a minute or two, just in case you have to, if you have some questions about this first part. I can take questions if you have some. If not, we can continue, of course.
So we have a question here from one student.
Okay.
Hello, Patrick.
Hello.
Yeah, please, my question is, you were talking about the clocks not being synchronized at each observatory. So if they are not synchronized, then how then do they observe or track a source that they are interested in together?
Okay, well, maybe I was not, when I mean not synchronized, I mean they are synchronized up to maybe, well, below a microsecond of time. So they probably are synchronized at the level of maybe 100 nanoseconds, which means that this is already, they are quite synchronized. But for the analysis, you need to have something which is much more than that. You need to go at the level of 10 picoseconds, something like that. So if from the analysis, VLBI analysis point of view, they are not, the synchronization is not enough, it's not high enough. But to do the observing, of course, they observe, I mean, this is in 10 to minus 7 or 10 to minus second. So just to do the observation at the same time, this is enough. Is that clear?
Yes, it's clear, but then it means that when they are deducing the data, do they factor that little gap in there? Do they calculate that delay, time delay in there?
Actually, this is what I'm going to explain. Actually, the difference, you estimate the difference. You estimate the difference between the clocks because you don't know, you cannot model them well enough because they are not fully synchronized. And actually, the difference between the clocks due to the number of observations you have, the number of sources you have in different parts of the sky, you can infer from the analysis the clock parameters.
Okay, thank you very much.
Thank you.
Thank you, Patrick. You can continue.
Okay. So now getting into the modeling. So the VLBI delay model, so the tau-m that I mentioned previously, consists of several terms. So the major terms is what we call the geometric delay. And this geometric delay just represent the time delay. I mean, if you look at this graph, your sources is there. You have two stations here, one here. Then you see that the signal coming from that source arrive first at this station and then at the second station with some time delay. So this is the geometric delay. If there were no atmosphere, nothing else, this would be exactly like that. And this delay depends on the direction of the source, which I call here vector k, and the baseline vector between the two stations. Actually, it is the product, the vector product between these two quantities with some scaling factor due to the speed, c is the speed of light. And so if you are, and this quantity is measured, this is your measured quantity, this comes from the correlation from this is your observed quantity. And then in order to model this, you may think that this is simple, but in fact, the two vectors are not in the same reference system. One is represent the direction of your quasars, and the other is on the vector. The other vector is on the ground, so it moves with the Earth because the Earth rotates. So this geometry is always changing. So you need actually to transform this B in the terrestrial frame to the same vector in the celestial frame, where where the vector k is known. And you have a matrix transformation, which is called Q, which takes into account the rotations of the Earth's rotation to do this. I will not go into details, but besides this transformation, you need also to apply some corrections to your vector B, because your positions are not fully stable. You have tectonic motions, so you need to correct for this. You have tides. You have what we call ocean loading. This is also related to tides and something related to the atmosphere. So basically, you need to apply a number of corrections to your baseline vector known with respect to the Earth center to do this. So I will just briefly explain all these corrections that you have to apply to this vector. So, okay, so as I said, I'm going to talk about this now. So you have tectonic plate motions. As you know, you have tectonic plates on the Earth, and these moves at the level of a few centimeters per year. So you need to account for this because the positions that you measure are typically below 1 centimeter, a few millimeters. And if you don't account for these tectonic plate motions, then you will not get the proper accuracy. But you have also earthquakes, the earthquakes. And then when you have an earthquake, you see on this map the distribution of earthquakes that were used for constructing what, as we will see later, the International Terrestrial Frame, the 2014 version. And when you have an earthquake, it just creates some break in your position. It can move by several centimeters. In some occasion, it was even 10 or 20 centimeters. So you need to account for this. Otherwise, this will not be precise enough. Tidal effects. So just briefly, the Earth is an elastic body, so it can deform due to tidal effects. And just to explain this effect with simple figure, you have basically these effects are due to the moon and the sun. And the gravitational attraction depends on the distance from the attracting body to your body. And since the distance, for example, here and here is different, it means that this part of the Earth will be attracted more than this one. And then this creates this kind of figure. So the Earth deforms in this direction. So, and then, of course, all this depends on the position of the moon, the position of the sun, and things. So this get mixed. But basically, this is the principle of this effect. You have, due to the Earth's rotation, and you have, they happen basically at two frequencies. One per day, so one cycle per day, and twice a day. So basically one every 12 hours or every 24 hours. Roughly, there are some slight variation because it depends on a number of things. But this is basically, you have also longer variations which are due to the planets, but it's lower. Okay, another effect which is still due to the fact that the Earth is not a rigid body but is an elastic body. It's what we call the pole tide, and it is the axis of rotation of the Earth slightly moves with respect to the Earth's crust. This is the projection of the axis on the North Pole. Basically, at 0, 0, you have the North Pole, and this shows over some 30 years the displacement of the axis of rotation with respect to the Earth's crust plotted on the North Pole. And if the axis is not at the same place, if the rotation does not happen around the same axis, then it creates also some changes in the deformation of the Earth. And this effect is what we call the pole tide, and this is the elastic response of the Earth's crust to shift to the spin axis of orientation. So this is a second order effect, but you need to account for this at the centimeter level. Another thing, also a secondary effect, is the effect of what we call ocean loading. Due to the tides, the ocean masses are not, they move. I mean, the masses move, the ocean moves within the masses of water moves in the ocean. And this creates also some variation in the attraction to your stations, which are on the Earth's crust. And so this moves the observing stations at the level of a few centimeters. So you need to account for this, and this depends also on whether you are closer, your sites are closer close to the ocean or further away. Another small thing, atmospheric loading. Depending on the pressure, you have the atmospheric pressure, depending on whether it's high or low, it will press more or less on the crust, and this will create also some small deformation, which are below 1 centimeter. You see that this is the level here of the deformation, and this is in millimeter. So this is a deformation of a few millimeter level up to 1 centimeter. But if you want to get sub-centimeter accuracy, you need to account for this. And final thing I wanted to mention, it is the post-glacial relaxation. Some 10,000 years ago, there were thick ice sheets over Northern Europe, Scandinavia, and Greenland and Canada. So there were considerable pressure weights on the Earth's crust, but this ice sheet melted, and so there is some relaxation effect, which means that the Earth's crust is still moving up slightly due to this effect that were removed to the sheets that were removed some long time ago, but there's things are still moving up. Okay, so I finish with the first term, the geometric delays, as I explained. So I give you a brief description of the tectonic motion, solenoid, earth tide, ocean loading, pole tide, atmospheric loading, basically all the effect that you would have to consider if you want to model things as best as possible. So now moving to the second parameter. The three other parameters are somewhat simpler. So I'm going to talk about the instrumental delay now. And this is caused basically by two effects. First effect, as I said earlier, and as we discussed with the previous question, the clocks are not perfectly synchronized, so there is a small difference between the clock at the two stations. So this is one effect, and there is also another effect, which is called by the propagation in the cables and electronics at each antenna, because the cables and the electronics, I mean, the cables do not have all the same length at one station or at the other stations. At least you cannot guarantee that. So this means that there will be a differential effect due to these time delays in the cables. So in practice, it's difficult to separate these two effects because they mix, they have the same signature. It's a difference, it's a like difference in time. And so in practice, you don't try to model this, but you just estimate an overall instrumental effect, which is actually the sum of the two effects, the clock difference and the difference in the propagation in the cable and electronics. And you just estimate this as a linear or quadratic function where you estimate, so you estimate a clock offset and a clock rate, even though it includes also the other effects. But basically, this is a parameter that you don't try to model, but it comes out from the least square estimation. Okay, so there are the geometric delay, the instrumental delay, but then you also, your signal, when you reach the station, also cross the atmosphere. And there are two parts. I mean, you are affected by two parts. First, the troposphere, which is the layer that is the closest to the ground, and then the ionosphere, which is higher in altitude. And they have different effects because the ionosphere is composed of ionospheric electrons and includes a different delay. So first, the troposphere. So as I said, your signal cross some part of the troposphere at one station or at the other station, but because you have clouds and different effects, it's not the same. And since you have distant antennas, if one antenna is on continent and the other antenna is on another continent, of course, this is due to the meteorological effect too. So it will not be the same thing at the two stations. So actually, what you need to account is the difference between the two effects, between the two stations. And besides that, there are two components in the tropospheric delay. One that you call the dry component, which you can model at some level from the meteorological data using pressure and temperature. You can model this effect at some detail, at some reasonably accurate level. But there's also a wet component, which depends on the vapor. The water vapor content in the atmosphere, and this one is difficult to model, and it is very variable. So what you do is that and another thing that I mentioned, that it depends also on the elevation. Depending on whether your antenna observe at high or low elevation. If you observe at zenith, for example, you will cross a smaller part of the troposphere than if you observe at lower elevation, because you will cross a longer part. So it depends on your direction of observing, your elevation, the elevation of your antenna at each. And it's different at each site, of course. So what you do, the modeling, the principle is that you estimate, well, you model the troposphere at zenith, and then knowing the value at zenith, you just use what you call a mapping function, which depends on the elevation angle to get the value at the elevation angle of your observation. So you just multiply the zenith value by this mapping function. And as I said before, this is a differential effect. The value at one station minus the value of one at the other stations. And as I said also earlier, it's difficult to model because it's the wet component is very variable. So this is also one quantity that you estimate in your analysis. And just to give you a feeling about what is a mapping function. So a mapping function can be like this. This is a basic one. So it depends on the sinus or the elevation of your antenna at your site. And then you have coefficients which have been calculated over the years in various ways. It can depend on the latitude, the height of the station, the day of year, because it may depend on seasons. And you also can infer these coefficients from numerical weather model, where they are determined empirically from actual data from these models. And then all this, so you have different mapping function. And so over the years, you get different things. And what we usually use now is mapping function built from the Vienna group. That's why it's called VMF, Vienna mapping function. So if you hear this comes from Vienna. There are also several versions which become more and more complex. Okay, so I will finish this overview of the modeling with the ionospheric component. So the ionospheric component depends on the electronic content of the atmosphere. And the electrons, this is due to ionization by the sun. So it's high during the day at the local site and low during the night, because it's the sun doesn't ionize the atoms. And one thing is that it is proportional to the inverse of the squared frequencies. And it's, as for the troposphere, it is also a differential effect. So you need to difference the value calculated for one station to the value calculated for the other stations. But the nice thing is that this quantity, which is also very difficult to model, is proportional, as this proportionality to the 1 over the square of the frequencies, which means that if you observe at two frequencies which are well enough separated in gigahertz, and usually we use S-band 2 gigahertz and X-band 8 gigahertz, you can just eliminate the effect by a linear combination. And this is what is explained on this slide. Your ionospheric, your delay includes some ionospheric effect, which is, as I said, proportional to the inverse of the square frequencies. So this is the delay measured at one frequency and the delay measured at the other frequency. And tau is the delay, would be the delay if there were no ionospheric effect. But you see that you can, from these two equations, you can get tau by applying a linear combination of these two quantities, the delay measured at one frequency and the delay measured at two frequencies. So tau nu one is S-band and nu2 is X-band. And then you get a delay free of ionospheric contribution, and you get here this gives you the coefficients A and B, which is a combination of the two frequencies. So ionospheric delay is a problem, but in fact it is not in the end, because you remove it from the observation. Of course, if you would observe at a single frequency, you would need to model this. Okay, so I will perhaps I will stop for, yeah, I may stop for a few minutes if you have some questions about the modeling.
Patrick, they currently don't have any questions if you want to continue.
Okay, we can continue. So geodetic VLBI product. So I already mentioned this a little bit. So as I said, you basically have three products. So I will start from the Earth and then move to the sky. So the first product is the terrestrial frame. And usually all this is, there are, I mean, standards so that everyone use the same frame. And the current one, well, this standard is what we call the ITRF, International Terrestrial Reference Frame. And the current version is ITRF 2014, which means that this was done around that time. So it is already somewhat old, but a new one is in preparation and it will be available soon. So the ITRF gives you positions of all geodetic stations on the Earth. So this is in a X, Y, Z coordinate with respect to the center of the Earth. So this map shows all the sites for which you have positions, including SLR, GNSS, DORIT, and the VLBI. The VLBI site are shown with stars, orange stars. So you can see where the VLBI stations are located. Of course, there are many more things in the northern hemisphere than in the southern hemisphere. And in the southern hemisphere, there are only a few, well, limited number of VLBI stations in the southern hemisphere. Okay, so this is for the terrestrial frame. Well, okay, this was the positions, but as I said, they are not only positioned because the stations move. So you have also a velocity field, so horizontal velocities and vertical velocities. So you see here, so the horizontal components, the horizontal velocities are due to the tectonic motions, which you can see very well on this map, which shows and the scale is, I think, this is 2 centimeter, well, this bar is 2 centimeter per year. So you see that this can go up to probably up to the order 8 to 10 centimeter per year, the largest motions. And as I mentioned previously, when I discussed post-glacial rebound, you may have also some velocity components. And actually, you can see here this post-glacial rebound where you see the stations actually moving up in Northern Europe, but also in Greenland and in Canada. So this is not a modeling. This is the measurement of these results from the observation, and the scale is 5 millimeter per year. So you see that up to 1 centimeter, you can have motion up to 1 centimeter. On the other hand, if you are in some other part of the globe, then you have not much motion. I mentioned also there also you can see from the data some non-linear motion. You see there are possibly some seasonal signals at some station, which you can see. This is an example for a station in Brazil, which shows, it gives you are you okay? Are you back? Can you hear me? Can you hear me? Is it okay?
Yes, you should. Let's use the Wi-Fi first. It's okay. It's okay, Patrick. You can continue.
Okay, I'll continue. I thought you were
All
done.
right.
Okay, so I was saying that there were some seasonal signals at some stations due to some, we actually do not know why, possibly some meteorological effects, seasonal effects. And this can be, so you see the motions in east, north, and up at a station in Brazil. So you can see you have some effect at the level of few millimeters horizontal and higher in vertical. So apart from the seasonal signals, you have also some, I mentioned the earthquakes. And following an earthquake, basically when you have an earthquake, you have a break in the position. So the positions of a site move by several centimeters or more. But when it's done after the earthquake, it doesn't get back to exactly the same velocities, at least not for some time, because there is some delay and possibly some deformation. You see here on the right that you have some nonlinear effect, especially in these two components. And then probably if we continue to observe, then we will get the same velocity at some point, but it will take time. So you need to account for these deformations, which are not linear. Okay, so this was for the terrestrial frame. Second product, the Earth orientation. So first, the parameters having to do with the Earth's rotation axis. So on the left, this is an illustration of the motion of precession of nutation. So the precession is the long-term motion of the axis of rotation of the Earth with respect to space, with respect to the sky, and the nutation is a small oscillation on top of this long-term motion. And you can measure this very precisely with VLBI, and actually these motions depends on how the Earth is made, because the Earth is not uniform, and you have a core in the middle, and depending on the shape of the core, on some geophysical parameters, this affects the nutation motion though. So by measuring precisely this motion, you can infer something about the Earth's interior. So this is for space, and as I said before, the axis of rotation also move with respect to the Earth's crust, and this is what we call polar motion. So this is the same thing, except that if I get back to this graph, you will see this axis changing with respect to the crust. So for example, maybe it can be here, and then you have some effect that you need to account also in your Earth orientation parameters. And the third thing, talking about the Earth orientation, is the variation in the speed of the Earth, or we call this also the length of day. So the Earth speed is not, the Earth rotation speed is not fully uniform. It varies at the level of 1-2 milliseconds, or at smaller levels too. And some part is not predictable because it depends on things happening in the atmosphere. And so this is why you need to measure. So on this slide, you have the long-term trend. So you see this is 1 millisecond. So you have an overall effect about 2 to 3 milliseconds. You have seasonal variations because it depends on the yearly effects, and then you have, if you remove this and remove this, you get something that is not noise, but which reflects the irregular variations of the Earth's rotation, and this is what you measure. Okay. Last product, the celestial frame. So the celestial frame is made of the position of a number of sources, extragalactic sources, which are very far away, the quasars. And so far, we have about more than 4,500 sources for which we measured their position very precisely. And by very precisely, this is at the level of 0.03 milliarcseconds or 30 microarcseconds in the right ascension and declination. So this is very precise. And this was obtained thanks to all the geodetic observations that have been carried out over the almost 40 years since the end of the 90s. So this is almost 40 years. You see here the distribution of the uncertainties. So the blue one is for right ascension, and the orange one is for declination, and this is the purple one is the part common to the two. And this is 0.1 milliarcseconds. So the most precise sources are in there, but overall they are the level of all the sources, apart from this one, are the level of 0.142 milliarcseconds, which is quite good. I should mention too that this frame, which is based on SX observations, as I mentioned previously, there are also two other catalogs. One that was made at K-band, so 24 gigahertz, and which includes 800 sources, and that was observed at even higher frequencies, 32 gigahertz, actually a combination of X and Ka band, 32 and 8 gigahertz and 8 gigahertz. And this one has also about 700 sources. And this is the official frame that people must use, so that everybody works in the same system. And this frame was adopted by the International Astronomical Union a few years ago in 2018. So this is the actual reference in the sky in the same way as, and this is called ICF3 because this is the third version. The first version was made in 1998. The second version was in 2009, and the third version in 2018. We do this roughly every 10 years or so. Among these sources, there is a small set which we call defining sources, and these sources have been were selected from the larger set in order to have a uniform distribution of the sky. These are sources that are very stable position and that are very compact sources, because the sources have some sources are more or less extended, but we choose very compact sources to select these defining sources. And the reason, the reason for these defining sources, the defining sources are those sources that really define the frame, that define the axis of the frame, which means that if you do another ICRF in 5 or 10 years, you will use those defining sources to align your new frame to the previous frame, because it's important to keep the same orientation in the sky. Okay, so I discussed the VLBI product. So I'm now going to move to the final part, and where we talk about the future. Well, present and future actually, because this is already started. So some years ago, there were some prospective discussion, and in order the goal was to reach 1 millimeter accuracy in the position of the geodetic sites on the Earth. And so this is a goal that we want to achieve. And why achieving this goal is because if you go to the 1 millimeter level, then you have access to a number of geophysical effects, global in connection with global changes, because it will depend on some pressure, some small variations of the position of the site due to pressure, due to humidity, due to winds and oceanic current, which can affect the site have an impact on the position of the site at this level. So there were some brainstorming that was done to see how we can achieve this. What I should have said is that the current precision is roughly at the level of sub-centimeter, but maybe 5 millimeter or so, and we are not really at the 1 millimeter level. So the conclusion from this design study was that if we want to reach the millimeter level, we need to increase the number of observations that you make every day, roughly by 1 order of magnitude, at least 1 order of magnitude, which means that you need to multiply the number of observations by 10 every day. So how could you do this? And actually, if you look at the network that we have today, usually it's large antennas, 20, 30 meters. This is this order of the order of the side of these antennas, and they move not that fast, which means that when you move from one part of the sky to the other part of the sky, it takes some time, sorry, because these are big instruments, and then you cannot move them very fast. Which means that during a 24-hour session, for example, you will spend a large part of the time where you don't observe, but you just move from one source to the next. And this is or the other half of the time. And for some stations, for some slow antennas, it's even larger than that. It can be 60, 70% of the time that you spend moving from one source to the next. So where you don't observe. So the conclusion that if you want to increase the number of observations, you need to have antennas that move faster. And if you want to have antennas that move faster, the antennas must be smaller, because you cannot move a big dish very fast. So the conclusion was that you would like to have antennas that are roughly 12, 13 meter diameter size, and you want to be able to move them with a velocity of 12 degrees per second in azimuth and 6 degrees per second in elevation. And if you achieve this, then this means that this means that each direction in the sky will be pointed within 20 seconds. So you will be able to move from one source to the next source, no matter where they are located in the sky, within less than 20 seconds. And then you will increase much more the number of observations during your day. And since you have smaller antennas, they have less sensitivity. So this will be compensated by observing a larger bandwidth. You observe. You don't observe as discrete frequencies, but you observe some bandwidth, and in your you record your signal with some width, and if you increase this, then you improve the number of bits in some way, and then you can get back to this to a reasonable sensitivity. So I said this is a project, but this is already it has already a reality, and some of these antennas have been constructed, and you see here some example in Spain, Germany, in Sweden, Spitsberg. This is in Norway, US, in Japan, and there are also some in Australia. So I would like also to mention that this is, I said that you use a wider bandwidth, but you also use you also observe at different schemes. This may be a bit complicated, but I will try to explain it. This is the frequency, and this is basically the phase that you observe. Today, you observe at X band, 8 GHz, and S bands. And you record roughly 500 megahertz bandwidth, okay? With the new VGO system, so VLBI Global Observing System, you will record the signal, you will with a band that is twice as wide as the current band, roughly 1 gigahertz. And then you will observe 4 such bands from 2 gigahertz to up to 13, 12 or 13 gigahertz. And so you have more signal recorded because the width is higher, but you will use also a different scheme to construct the observable using all the 4 frequencies and not just the 2 frequencies as S and X band. I will not go in detail, but basically this also increases the precision of your measurement due to this new observing scheme. So you get more observations, and you get observation also that are more precise. And then you can, this is when the network is built, we think that we should be able to reach the millimeter level. At least this is the plan. So this is the current situation of the VGOS network. So you see that in blue ones, in blue with the blue triangles show stations that have been built and which are currently operational, which means that they work not every day, but they can do observations. The red ones are stations that are built, but they are not yet operational. There are still some work to do at the station to make them operational and some testing. And the black one are those stations that are in planning stage, which means that some may be funded, so they will have some reality maybe in 5 years or more, and some of us are still at the project stage. So we will see if they are really built at some point. Some will, some probably will not, depending on the funding that the institute or the countries get to do this. And what I wanted to say is that this network with the blue stations has started regular observations about 2 years ago, since January 2020. There are 2 sessions, well, there are sessions every 2 weeks, regular session every 2 weeks with this new VGOS network, and it will be increased in the future. Also, well, it will become weekly, and then maybe even more than that. And adding also some station, I should say that the long term is to have a permanent network, which means that you will observe 24 hours a day and 7 days a week. This is the goal of this project, and this is and the reason why we want to do that is that you need to monitor the Earth's rotation all the time, because it is not predictable. So if you need to have some kind of permanent network. So we are not yet there, but we are progressing along this goal with, as you see on this map, there are already a number of stations. And the red ones will be operational within a few months, from a few months to a few years, I think. And then at some point, the number of sessions will be increased towards possible full permanent observing in maybe 5 years or so. And I think this was my last slide. So I will have, if you have some questions, I'd be happy to answer these questions.